In May 2025, the world witnessed a dramatic demonstration of modern missile defense systems during a major international conflict. Israel launched a sudden attack on Iran, prompting a large-scale retaliation and providing a rare, first-hand look at how layered missile defense operates under real-world conditions. At the forefront of public attention was Israel's Iron Dome system, widely recognized for intercepting short-range threats like unguided rockets. However, Iron Dome is only the first line of a much more complex, multi-tiered defense architecture. Each Iron Dome battery costs approximately $100 million, and each interceptor missile costs around $40,000, relatively inexpensive when compared to the U.S. Patriot missile system, whose interceptors can cost upwards of $4 million each. Recognizing the appeal of Israel's layered defense strategy, the United States has begun developing a similar framework, dubbed the Golden Dome. However, the scale and threat landscape faced by the U.S. is vastly different, and building a defense system that covers such a large territory introduces enormous technical, financial, and strategic challenges. The most basic threats faced by missile defense systems are crude rockets like the Chasm low-tech, unguided projectiles that cost as little as $800 and are often homemade using basic chemical propellants. On the other end of the spectrum are hypersonic glide vehicles, advanced weapons that travel at extreme speeds, can maneuver mid-flight, and are capable of evading traditional missile defense systems. While the Iron Dome was designed primarily to intercept the former, the Golden Dome must contend with the latter long-range, highly maneuverable, and far more dangerous missiles. The proposed Golden Dome will be a vast, multi-layered network designed to protect the continental United States from threats ranging from short-range cruise missiles to intercontinental ballistic missiles and hypersonic weapons. The system's projected cost ranges from $161 billion to as much as $542 billion over the next 2 decades, potentially rivaling or exceeding NASA's total budget over a similar period. To understand how such a system functions, it's important to break down missile defense into 3 key stages: detection, tracking, and interception. These stages align with a missile's 3-part trajectory: boost phase, mid-course phase, and terminal phase. Detection often begins in space, using infrared sensors capable of spotting the intense heat signatures emitted during a missile's launch. The U.S. relies on the Space-Based Infrared System, SBIRS, which includes satellites in both geosynchronous and highly elliptical orbits. These provide near-continuous coverage of critical regions around the globe. Once a missile is detected, its path must be tracked in real time to determine whether it poses a threat. This task involves a global network of ground-based and space-based radar systems. One of the most advanced is the Long-Range Discrimination Radar, LRDR, in Alaska, built using gallium nitride technology. It can operate at multiple frequencies for long-distance tracking and high-resolution imaging. Its role is crucial during the missile's mid-course phase, when decoys and multiple warheads may be deployed to confuse defense systems. Interception is the final and most difficult stage. Unlike traditional explosives, modern interceptors rely on kinetic energy colliding directly with incoming warheads to destroy them. Explosives are less reliable at high altitudes where the lack of atmosphere limits their blast effectiveness. And given the high speeds and evasive maneuvers of some modern weapons, interception requires a highly accurate, split-second response. Modern interceptors are guided by advanced sensors, such as arrays of infrared photodiodes that generate thermal images to lock onto targets. These are mounted on missiles like those used in the terminal High Altitude Area Defense (DOD) system or the Navy's Aegis-equipped destroyers. The F-35 fighter jet also plays a critical role, acting as a flying node in the defense network. With its powerful sensors and stealth capabilities, the F-35 can detect threats earlier than ground systems and even engage missiles directly if necessary. But the Golden Dome is intended to go beyond existing systems by prioritizing the defense of civilian infrastructure, concept referred to as counter-value targeting. This strategy focuses on shielding population centers and critical infrastructure, not just military assets. It suggests a shift in policy, defending cities like New York, Los Angeles, and Houston as top priorities. This approach poses difficult political and ethical questions. Which cities are worth protecting? What threshold of population or strategic importance must be met? And how will local communities respond when a missile defense system suddenly appears in their area? Each layer of the proposed Golden Dome plays a specific role. That intercepts high-altitude ballistic threats. The Patriot system defends against lower-altitude threats like cruise missiles and drones, using radar-guided missiles like the PAC-2, which detonates near its target, and PAC-3, which destroys targets via direct impact. While these systems have been battle-tested in places like Ukraine, they're expensive to operate and have limited coverage. Rapid deployment across the U.S. would be prohibitively costly without more mobile or scalable solutions. This is where the executive order's most controversial component comes in: intercepting missiles in the boost phase or even before launch. This requires placing interceptor weapons in low Earth orbit, fundamentally changing the balance of power in space and triggering concerns over weaponizing space. The only practical way to guarantee boost phase interception anywhere on Earth is by stationing a constellation of kill vehicles or directed energy weapons in orbit, ready to react in seconds. Similar ideas have been proposed before. In the 1980s, President Reagan's Strategic Defense Initiative (SDI) included programs like Brilliant Pebbles, which proposed small autonomous interceptors stationed in orbit, although the program was eventually scrapped. The idea has been revived in light of today's dramatically lower launch costs and the increasing feasibility of satellite constellations. SpaceX's Starlink, with over 7,000 satellites in orbit, has already proven the viability of such large-scale deployments. While kinetic interceptors in orbit may be effective, they come with high costs and the potential for dual-use or offensive applications. Lasers offer a potentially less controversial alternative. High-energy lasers can destroy missiles by heating critical components until they fail. These systems have already been tested on platforms like the modified Boeing 747 Airborne Laser Testbed, which successfully intercepted missiles during their boost phase. Future space-based versions could provide similar capabilities from orbit. However, lasers require significant power. A single high-power space laser could require 250 kilowatts to 1 megawatt of energy. The International Space Station, for comparison, can only generate around 120 kilowatts on average. Meeting these power needs may involve creating a second orbital. Infrastructure: geosynchronous solar power stations that beam energy via microwaves to where it's needed, allowing interceptor satellites to remain small and operate in standby mode until activated. Still, this raises serious technical and geopolitical concerns. Would such weapons violate international treaties or be interpreted as offensive threats? Would adversaries preemptively attack these systems? Anti-satellite weapons already exist, and a war in space could disrupt not only military satellites, but also commercial and civilian networks. Financially, the Golden Dome faces an uphill battle. The initial funding, $25 billion, has been tied to a much larger $150 billion defense package still moving through Congress. Without this funding, the project could stall, just as similar programs did in the 1990s. Even if approved, the full build-out could cost over $500 billion, forcing trade-offs with other national priorities. Politically, both China and Russia have voiced strong objections, calling the plan destabilizing and warning it could trigger a new arms race in space. These concerns are not unfounded. A full-scale missile defense system with space-based interceptors could theoretically give the U.S. first strike capability without fear of retaliation, upsetting the current global strategic balance. In short, the Golden Dome is an ambitious effort to rethink national defense for a new era of missile threats. It builds upon existing technologies like THAAD, Aegis, and Patriot systems while integrating new components from satellite-based lasers to orbital kill vehicles. But its success will depend not only on technical innovation, but also on political will, international cooperation, and a careful balancing of security needs with global stability. Whether the U.S. can build such a system and whether it should remains an open question.